Good evening, everyone. So today, good evening, everyone. So welcome to my YouTube channel, Math Avatarm. Okay. So hope you are good. So today, in last lecture, we study uniform continuity, and we have done one lecture on that. So today we are going to study uniform continuity. We are continuing this topic with lecture 2. Okay. Okay. So in last lecture, we have given some examples of uniform continuity, continuous functions, and we have proved some theorems. Okay, by using that, we have shown that some functions are uniform continuous, like sine, cos, sine square x, cos square x, mode function. Okay, all these functions. Now, in this lecture, we give some examples of uniform continuous functions which are not uniformly. In this lecture, we give examples of functions which are not actually uniformly continuous functions, even they are continuous functions. Okay. So let's start. Okay. So we prove a result. Okay. We start with a theorem. We start with a theorem. Let f I to r be a function. Then the followings are equivalent. Followings are equivalent. Number first, f is uniformly continuous. Second one, fxn minus fyn absolute tends to 0 whenever xn sequence and yn sequence, both sequence are in interval such that their difference tends to 0. Okay. So second statement is, you take any two sequence such that their difference tends to 0, then images, the difference of images also tends to 0. So these two conditions are equivalent. Statements are equivalent. Okay. If f is uniformly continuous, you take any two sequence whose difference tending to 0, the corresponding image sequence will tend to 0. Or if image sequence is tending to 0, whenever you have two sequences, their difference tending to 0, then such function will be uniformly continuous. Okay. So let's prove this result. Okay. So proof. So one implies two. One implies two. It means we are assuming that our function is uniformly continuous. Okay. And we are going to prove second statement. Okay. 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 So let xn and yn are two sequences such that their difference tends to 0. Okay. Okay. So let epsilon greater than 0. Okay. Since f is uniformly continuous, we have delta greater than 0 such that fx minus fy absolute value less than epsilon for all x and y belongs to I with x minus y difference less than delta. Okay. Now xn minus yn tending to 0. What does it mean? This implies there exists capital N belongs to natural number such that xn minus yn will be less than delta for all n greater than equal to capital N. Okay. Now, therefore, let's say it 1. Let's say it equation number 1. You see that xn yn difference is less than delta. So by uniform continuity definition, their image difference will be less than epsilon. So therefore, what we have? Therefore, from 1 we have what we have fxn minus fyn less than epsilon for all n greater than equal to n. What does it mean? You have taken an arbitrary epsilon and you have find a sum capital N belongs to natural number such that this holds. What does it mean? It means fxn minus fyn difference tending to 0. So we are proved. So we have proved statement second. Okay. Now we have proved 1 implies 2. Now we are going to prove 2 implies 1. So 2 implies 1. 2 implies 1. Okay. 2 implies 1. So we are considering the statement second and we are going to show that f is uniformly continuous. Okay. F is uniformly continuous. Okay. Okay. So we are considering this by we are going to prove this by contradiction. If possible, suppose that if possible, suppose that 1 is not true. It means, what does it mean? F is not uniformly continuous. Okay. Uniformly continuous. So it means, so mathematically what does it mean? It means there exists some epsilon greater than 0 such that no delta greater than 0 exists satisfying fx minus fy less than epsilon for all xy belongs to I such that x minus y less than delta. Okay. So there is some delta for, there is some epsilon greater than 0. For that no delta exists. What does it mean? It means if I take my delta n is equal to 1 by n greater than 0, then there exists 2 points xn and yn belongs to I such that fxn minus fyn is greater than equal to epsilon, where xn minus yn less than 1 upon n. Okay. So take this sequence and this sequence in I, and what is, they have property this one. So when n tending to infinity, this will go to 0. So what does it mean? But fxn minus fyn is not tending to 0 because their difference is greater than equal to epsilon. So this sequence cannot tend to 0. Okay. So this implies, which is a contradiction to 2, because we have considered that 2 is true and we are going to prove 1, and therefore 2 implies 1 is correct. So both these statements are equivalent. Okay. So why we are proving this theorem? Why we are proving this theorem? We are proving this theorem because we want to give examples of some functions which are continuous functions, but they are not uniformly continuous functions. So see this example now. You see this example. So see this example. F(x) is equal to x square. Okay. On R. So this function is continuous on R. We will prove that, but this is not uniformly continuous on R. So this function is not uniformly continuous. Is not uniformly continuous. Okay. So we know that by theorem we will, if we can find two sequences, xn and yn, their difference tends to 0, but the image of the corresponding image difference is not tending to 0, then this will be solved, this will be proved that function is not uniformly continuous. Okay. So I am taking this sequence. Xn is equal to under root n plus 1 and yn is equal to under root n. So what is this? Xn minus yn difference. So what is this? Because this is positive quantity, so we can skip. Okay. Now I can multiply and divide by this. Okay. So what I will get? A square plus b ka whole square formula you apply here. So this is n plus 1 minus n upon n plus 1 plus n. So n will be cancelled out. So this is 1 upon n plus 1 plus n. So my xn minus yn difference is equal to this. So obviously this tends to 0 as n tending to infinity. So I have find two sequences, their difference is tending to 0. Now let's see their image sequences differences. So fxn minus fyn, what is this? This is n plus 1 ka whole square minus absolute under root n square. So this is n plus 1 minus n will be cancelled out. So this is 1. But this can never tends to 0 because this is constant quantity as n tending to infinity. So this implies f is not uniformly continuous on R. Okay, f is not uniformly continuous on R. Similarly, you see second example. Example 2. Similarly, if we take fx is equal to x cube on R is also not uniformly continuous on R. Okay, how you now you what will be your choice of xn? What is the choice of xn? Xn is choice, you take this choice, and yn choice you take. Okay, so what is the difference? Xn minus yn. So this is n plus 1 upon q n q. So what I will do? You multiply by n plus 1 ka 2 by 3 plus n 2 by 3 minus plus n plus 1 by 3 and 1 by 3 upon n plus 1 2 to the power 3 to 3 by 2 plus n to the power 3 by 2 n plus 1 1 by 3 and 1 by 3. So what will be this? AQ minus BQ formula you apply here. So what you will get? N plus 1 minus n plus 1 2 by 3 n to the power 2 by 3 n plus 1 1 by 3 n to the power 1 by 3. So n and n will be cancelled out. So what is this? 1 upon n plus 1 to the power 2 by 3 plus n to the power 2 by 3 n plus 1 to the power 1 by 3 n to the power 1 by 3. So what is the xn minus yn is this. So you see that in denominator n things are coming. So this also tends to 0 as n tending to infinity. Okay. Now see image sequences, difference of image. So fxn minus fyn, what is this? This is n plus 1 minus n. This is 1. That is not tending to 0 as n tending to infinity. This implies fx is equal to x cube is not uniformly continuous on R. Okay. So fx is equal to x square, fx is equal to x cube. Both are not uniformly continuous on R. but these functions are continuous on R, but not uniformly. So what we got? Remark. Fx is equal to x square and dx fx is equal to x square and fx is equal to x cube are continuous functions on R, but they are not uniformly continuous on R. Okay. So we have examples of continuous functions which are not uniformly continuous, that are fx equal to x square and fx equal to x. Okay. Now, in last class, I have seen that in last class of same topic, uniform quantity, lecture 1, I have seen that fx is equal to x, fx is equal to x is uniformly continuous. Okay. Okay. In last class, I have seen this one. This fx is equal to x is uniformly continuous on R. Okay. So what we got actually? So I am asking one question. This question may come in a competitive exam. Let fx is equal to x to the power n, where n belongs to n. Then which of the following statements are correct? Number 1, f is uniformly continuous when n is not equal to 1, f is never uniformly continuous third one, f is uniformly continuous on R. Okay, on R, uniformly continuous on R if and only if n is equal to 1. Fourth one is none of the above. Okay. So we have this question. Fx is equal to xn, where n belongs to a natural number. Then which of the following statements are correct? First option is f is uniformly continuous on R when n is not equal to 1. So we know that we already proved that when n is not equal to 1, fx equal to x square and fx equal to x cube are not uniformly continuous. Okay. So this option is not correct. F is never uniformly continuous, second option, but n is equal to 1, it is uniformly continuous. Okay. Third option, f is uniformly continuous on R if and only if n is equal to 1. So if n is equal to 1, then f is equal to x it is, and it is uniformly continuous. We take n greater than 1. So similar technique we can apply as we have apply in fx equal to x square and fx equal to x cube in showing that they are not uniformly continuous on R. So if n is greater than, same techniques can be done, and it can be proved that when fx equal to x to the power n greater than 1, it is not going to be uniformly continuous. Okay, so therefore fx equal to x to the power n is uniformly continuous if and only if n is equal to 1. So option this is correct. So all other three options are incorrect. So option 3 is correct. Okay. So today we have learned some examples of content function which are not uniformly continuous, and this we have proved by help of this theorem which I have proved in the starting of this lecture, that f is uniformly continuous if and only if you take any two sequences, their difference is tending to 0, then image sequence tends to. Okay, so this is very good result, and we have, by using that result, we have proved that there are some functions which are continuous but not uniformly continuous. Okay, so thank you very much for today's lecture. Please like this lecture, share, comment and subscribe. Thank you very much. We will see you in next class. Thank you very much.